Hello, I'm Sanat Khanna, and I worked alongside Owen Erickson and Catherine Howe for the Kinetics and Reactions Engineering project. Today I will be presenting the problem that we had chosen and the results and conclusions obtained from solving the problem. Our problem involved the isomerization of xylene. Okay, so a little bit about the problem that we were completing. As can be seen on the screen, xylene has three major isomers, these being metaxylene, orthoxylene, and paraxylene. This problem had two reactions occurring in series. The first reaction, going from M-xylene to O-xylene, can be classified as being reversible, and the second reaction, going from O-xylene to P-xylene, can be classified as being irreversible. Additionally, the problem specifies that a packed bed reactor using 100 kilograms of cryolite catalyst is being used, alongside a feed containing pure M-xylene at a flow rate of 2 moles per minute. The initial temperature of the feed was given as 330 Kelvin, and the total concentration of the feed was 2 moles per decimeter cubed. Using these conditions, we were asked to first plot concentrations of each of the xylenes down the length of the reactor. Since this problem employed a packed bed reactor, the concentrations were instead plotted as a function of catalyst weight and not length itself. Second, we were asked to find the lowest and maximum concentrations of O-xylene down the length of the reactor. Once again, this was done in terms of catalyst weight. Furthermore, we repeated the above questions for a feed of pure O-xylene instead of a feed of pure M-xylene, and were additionally asked to find the maximum concentrations of metaxylene in the reactor. And then finally, different system parameters were varied to see how the system would behave at these conditions. Okay, so since we had chosen a book problem to complete, much of the information relating the kinetics and rate expression values were given to us. As you can see on the screen, the heat formation values for the different reactions are given, alongside the rate constant expressions for K1, K3, and Kc. These expressions are a function of system temperature, which is changing at various points in the system. Hence, an energy balance must be performed on the reactor. The heat of reaction values are also given to us, and it should be noted that they are negative for the reactions that were employed in the problem, hence signifying that these are exothermic reactions. So for reaction 1, we have negative 1800 joules per mole, and reaction 3, we have negative 1100 joules per mole, and these are both in terms of the amount of O-xylene formed. The heat capacities for all the species were assumed to be constant at a rate of 100 joules per mole Kelvin. Additionally, a value of UA over rho B is given. This term will be seen later when the energy balance is performed on the reactor. It is used to relate the heat removed from the reactor due to convection. You may be more familiar with it as Q equals U times A times delta T. This is that UA term where U represents the overall heat transfer coefficient. In this case, it is just divided by the bulk density. So we have a value of this term being equal to 16 joules per kilogram per catalyst per minute per degree Celsius. So a little bit about xylene itself before we start getting into solving the problem. Xylene is a colorless liquid often used as a synthetic chemical, and it is widely used in many industries such as rubber, leather, and printing, and can be found in many products such as gasoline, cleaning agents, and pesticides. As mentioned previously, xylene has three major isomers, these being metaxylene, orthoxylene, and paraxylene. Amongst these three isomers, paraxylene is usually the most significant. It is often used in the process to make other prominent chemicals such as polyethylene terephthalate and dimethyl terephthalate. These chemicals are involved in the manufacturing of plastics, mold, and films. Hence, in our reaction, the production of paraxylene will be treated as a desired product. The catalyst being used in the packed bed reactor for this problem is cryolite. Cryolite is a colorless mineral that occurs naturally in many places around the world. It can also commercially be synthesized by the fusion of sodium fluoride with aluminum fluoride. A common application of cryolite is in the electrolytic production of aluminum, in which it is used as a solvent to enhance the properties of the reaction. I won't discuss too much about these things, but the main thing to take away is that cryolite is the catalyst being used in this reaction in order to transform xylene amongst its isomers. The first step in solving the problem was to perform a mass balance on the given system. Following the general guidelines for the design equations for a packed bed reactor, the mole balance on species A, B, and C, where A is metaxylene, B is orthoxylene, and C is paraxylene, are presented on the screen. These equations assume that the reactor is operating at steady state conditions. So we have dFA dW is equal to RA, dFB dW is equal to RB, and dFC dW is equal to RC. So the next step was determining the expressions for the rate law. The expressions for the rate law became a little bit tricky since two reactors were being employed, in which one was reversible and the other was irreversible. So we had to come up with a net rate for each of the species. Following the same notation presented previously, where A represents M-xylene, B represents O-xylene, and C represents P-xylene, the rate of formation of A will be equal to negative K1 times Ca plus K2 times Cb. The rate of formation of B will be equal to negative K2 times Cb plus K1 times Ca minus K3 times Cb. And finally, the rate of formation of C will be equal to K3 times Cb. And the K represents the rate constant values you guys saw earlier, and C is the concentration of the respective species. The next step was to perform an energy balance on the reactor itself. The general form of the energy balance for a packed bed reactor can be described by the equation dT over dW is equal to Qg minus Qr all over the summation of the flow rate times the heat capacity of each of the species. The Qg term represents the heat generated from each reaction. This can be calculated by multiplying the heat of formation with the rate of formation for each of the reactions occurring. As mentioned earlier, the heat of formation values were defined in terms of the amount of O-xylene formed. Hence, the rate of formation will be in terms of O-xylene as well. Since reaction 1 and 2 were essentially the same reaction, the first just being the forward reaction and the second being the reverse, the heat of formation values were the same. The only difference is that the sign was flipped for the latter case. The QR term represents the heat removed from the reactor, and this is where the UA or ρB term described earlier shows up. So we have QR is equal to UA all over ρB times T minus TA, and T represents the temperature that is varying in the reactor with catalyst weight, and TA is the ambient temperature. If you combine everything together, we end up with the final equation you can see on the screen. Alright, so this is a summary of all the equations that we have just derived. The first three are the mole balances, and the last one is the energy balance. These four differential equations must be solved simultaneously along with the parameters presented with the problem statement. This cannot be done easily by hand and hence was performed using MATLAB code. More details on the MATLAB code and program can be found in the formal report of the project. I will next present the results obtained from solving the problem. Okay, so from MATLAB, we were able to obtain our results. This first figure shows concentration of each of the species as a function of catalyst weight for the case of a feed of pure M-xylene. The plot shows logical results since initially we have only M-xylene at a catalyst weight of 0 kilograms. As we go further down in catalyst weight, the concentration of M-xylene begins to decrease rapidly and the concentration of O-xylene begins to increase. Then finally at around 12 to 13 kilograms of catalyst weight, the reaction reaches equilibrium and the concentration of M and O-xylene are begin to decrease at a steady rate. While this is all occurring, the concentration of P-xylene is steadily increasing, and this makes sense because it was part of the third reaction which was irreversible. So the O-xylene is steadily being converted to P-xylene throughout the reactor volume. For the sake of completion, this table presents the maximum minimum concentration of each of the xylenes down the length of the reactor for the case of a feed of pure M-xylene. The problem only asks for O-xylene, but all the species are presented here. Additionally, the weight of catalyst where the maximum or minimum occurs is also presented. This next figure shows concentration as a function of catalyst weight for the case of a feed of pure O-xylene. Once again, this makes sense since at 0 kilograms we have only O-xylene present. As we move down the reactor, the concentration of O-xylene begins to decrease and the concentration of M-xylene begins to increase. At around 10 kilograms of catalyst weight, the reversible reaction reaches equilibrium and the concentration of M and O-xylene begin to decrease steadily, similar to the previous case. Once again, throughout the reactor, the P-xylene concentration is steadily increasing. Once again, this table represents the maximum and minimum concentrations of each of the xylenes down the length of the reactor for the case of a feed of pure O-xylene. The problem only asks for M-xylene, but all the species are presented in the table, as well as the weight at which the maximum or minimum occurs. As far as varying system parameters goes, we wanted to optimize the product in regards to obtaining a higher concentration of P-xylene. As I mentioned earlier, P-xylene was treated as a desired product and hence we wanted to increase the final concentration of the component in the final mixture, so that upon further processing and separation, the product would have a higher purity. Upon testing different flow rates, for the case of a feed of pure M-xylene, decreasing the initial flow rate was found to give a higher concentration of P-xylene in the products. This is because the species was spending more time in the reactor and hence have more time in order to perform the reaction and give a higher conversion. This figure on the screen shows how the concentration varied when the flow rate of M-xylene in the feed was reduced from 2 moles per minute to 0.1 moles per minute. As can be seen, the final concentration of P-xylene is significantly higher than when the original flow rate values were used. Another parameter that was varied in order to increase the final concentration of P-xylene in the mixture was catalyst weight. The initial problem only employed 100 kilograms of catalyst weight, but this did not give a very high concentration of P-xylene in the product mixture. Upon testing different values for catalyst weight, 3000 kilograms was found to be the optimal point. Using any more than this did not increase the concentration further, as the reaction had essentially gone to completion. The figure on the screen shows the concentration variation of the xylenes down the length of the reactor if 3,000 kilograms of catalyst was used. The one disadvantage of this is that this would require quite a large reactor since so much catalyst is being used, but depending on the process and company, this may be a sacrifice they make in order to get a more pure product. So to end off, I'm going to discuss a little bit about the safety and handling of the chemicals used in this problem. M-xylene has a flash point of 25 degrees Celsius, O-xylene has a flash point of 31 degrees Celsius, and P-xylene has a flash point of 25 degrees Celsius. These values indicate that the xylenes are flammable at standard conditions. Feed conditions for the process were given at roughly 57 degrees Celsius. Thus, care needs to be taken to ensure that a flammable mixture is not introduced into the packed bed reactor. The reactor should be designed inherently safe to mitigate any runaway reactions. So some things you could do are eliminate any ignition sources near the reactor, make sure storage tanks and reactors are properly sealed in order to prevent flammable vapors from escaping, and overall having good ventilation in the system will prevent a lot of these issues from occurring. Additionally, xylene has respiration, eye, and skin irritation effects. It can also be highly fatal if ingested. So care needs to be taken to keep exposure to workers at a minimal due to the toxicity of xylene. Workers should wear personal protective equipment at all times. So these were the resources that we used in solving the problem, and thank you guys for listening.